Oh, yeah, great. Okay, so today we get a step about memory effects, in particular within this triangle of relations that I started to introduce yesterday. And so I've just written it on the board now so that it's kind of sitting in there. I'll leave it up at the top for a bit as we get through more equations for today. On the right-hand side is just stuff that we talked about last time. So everything should have been written on the board before, but now at least it's there because we just want to use those equations and kind of run with them and see what they mean in some respects. So just to take a step back, if we look at the triangle, I've written down 3 iterations that we can talk about today. So with yesterday, all the stuff about super translations, super rotations, and this BMS story near null infinity was just so that it's more familiar and we can deal then with that, and also the already familiar case of just electric charge and some U1 gauge theory. And so hopefully we can kind of take insights from that to then look at the memory effects and soft theorems for the gravitational case and that light. Okay. Okay, so the first thing that I want to emphasize is the connection between null infinity and position space and momentum space that it gives us. So we had this picture before of massless scatters leaving at future null infinity and entering at past null infinity. So matching at spatial infinity, future time-like infinity, and past time-like infinity. And so we imagine some incoming particles, if we're thinking about massless scattering, along past null infinity, and some exiting ones in the future. And the point that if we look at the mode expansion for these radiative modes, we can actually see that along, say, this coordinate u, retarded time, it's going to be conjugate to the energy frequency. So if we have observables which are going to correspond to these memory effects which are associated with u integrals of these constraint equations, they're going to be long time integrated observables. So they're going to correspond to low frequencies. And then the saddle point approximation I'll show picks out the same direction. So basically, when we have a soft photon factor, like there's going to be a more momentum for this, like the actual soft particle. And we want to think of the direction that it corresponds to as being where you're sitting, like that points to from where this like acceleration of a charge is happening to as a far field observer in the radiation zone. So there's like a kind of position space observer interpretation. So I want to say that, say you have a soft photon going in this direction here, that would correspond to an observer sitting at large R and seeing the radiation zone fields from that guy. So there's a kind of nice position space interpretation, and we'll see that first of all by just looking at the mode expansions for the gauge fields. So let's look at a Z bar is the momentum. There goes to infinity. Z bar x mu. So I'm just going to change coordinates between the standard polarization vectors and some polarizations. And I'm writing out for the annihilation operator just to emphasize that I want to look at future null infinity. The coordinates are going to be at u. So at this point, the key thing to look at is just basically this part right here, the phase. So as R goes to infinity for finite u, this vector would have a large prefactor, and so the stationary phase approximation is going to pick out theta being 0. So theta is the angle between where the momentum of the plane wave is compared to the position, because we're literally doing a mode expansion of the position space field.
So, sorry, I just want to remember where this expression has come from.
This is just
So you've just taken like the expansion of the gauge field in bonding coordinates and then Fourier transformed it.
I've just taken the expansion of the gauge field like you'd see in a QFT textbook with here's the polarization, here's here, and then I plugged in bonding coordinates exactly like you're saying for that position x in flat place.
Okay.
So t is u plus r, so that u equals t minus r, and the spherical angle is just going to pick up the direction. So
yeah, just to understand, this is UR and coordinates on the sphere, coordinates in our
and sphere, so S2 coordinates. Right now, it's easier just to write the angle between them, but z's and z bars come in here when I'm converting, say, to the z bar coordinate. If I look at x mu here, when I plug in, I want to use z and z bar to get the right, just change the coordinate system. Okay. Great. Okay, so we have this mode extension. And now,
and what's the first symbol, the very first symbol after the equality sign?
is a charge. So normalization E, like sometimes if you put factors of electric charge, like unit electric charge everywhere, then it kind of pops up in different places. So we evaluate the stationary phase approximation for this guy, and you end up with the following. And I'll explain what this polarization tensor symbol means because it's a little bit interesting. Yeah.
All that is just electromagnetic potential, right? Expanded. So why are you taking derivative of x mu a?
Oh, this is like change of coordinates, right? So this is epsilon mu, and I'm literally just like evaluating how to change coordinates between mu as like t, x, y, z to the z bar component because I'm just interested in that component. And the fact I took r to infinity means that I'm looking at a particular limit.
What is written there is x mu contracted into a mu.
Yes, but it's d. This is like a sub z is equal to dx mu by dz. These are different coordinates. A mu.
Okay, it's
Like a change of coordinates because this x is like is what like t z as a function of the other coordinates. So it's just a change of coordinates. Okay. So we have this and a minus u. So the point of this is just to show that when you evaluate on the saddle point, you end up getting a Fourier transform just between the frequency and the retarded time coordinate in this limit. And so basically now, just looking at this expression, you're going to see that if we end up integrating over u or taking, so say we took a u derivative of this expression, we're going to pull down factors of energy. Integrating over u is going to basically pick out a delta function with support.
Can you explain this step?
Yeah.
So you're saying that this is stationary phase?
Stationary phase.
And then where?
So there's factors of like 1 over r that would come down to, but this is basically evaluating this at theta goes to 0. And so what happens here is this polarization tensor here is, say we write.
So this is another stationary point at theta equals pi?
This is, like when you look at this is the one that gets picked out. So, because at pi it would be, like you definitely want this to be 1, not -1 for like this large r. Otherwise you might be worried about incoming guys. Is that going guy? Is that what you're saying? So, right. This is r times 1 minus cosine theta. And so it's an order of, let's say if I were doing with incoming modes, say for instance the antipodal angle is kind of like this.
What's to evaluate this by stationary phase?
By stationary phase, I mean that this part is being set to 0 essentially, because r is going huge while we're keeping finite u. So, because like if I Taylor series it's really fun, you're going to say it's 0, and then if I plot theta, you're -1 on the other side, and that would be what would come up if you have, say you made it negative near a negative one, like you're saying, then in that case it'd be like u minus 2r, and that's going to shift you back to v. So we would say that that's the natural one for the incoming. No, but like you're right in the sense that if you change coordinates, it's a little bit of an order of limits thing going on here. Yeah, great. U versus V, and then this I'm looking at outgoing, so I'm like thinking of that as natural set of one. Great. Okay. And then there's one little subtlety in the sense that, say I just want to look at the polarization tensors for the sake of completeness here. So let's look at what we call the plus polarization in terms of. So I wrote up there what a formal momentum is in terms of energy EK and ZK. And right here, I'm going to write it in terms of the soft photon being energy omega Q, which doesn't affect this part, and position W. So that's just when I write W's, this is what I mean. With that. And so when I'm writing down this little hatted guy, I've actually evaluated it at the saddle point and taken the prefactor 1 over r away because I'm looking at kind of this gauge field mode and the particular mode of the radial expansion that I care about. So for instance, this becomes Z bar would be just looking at this coordinate transformation. And so then, in this case of my notation, epsilon plus c bar equals 1 over r times the above. So that just gives me, and also at w equals z from the saddle point. So this gives me root 2 over 1 plus c bar. Okay. And then one other thing to note is that, so basically z and z bar, you can see from this pick out plus or minus polarization. So in this case, we get this prefactor root 2, but if we did the same thing, if we evaluated ez bar of the minus polarization, then you would end up with the same setup for the expression, but evaluated with the other guy, and you'd get root 2 r z w c. So that this expression on saddle point goes to 0. So this right here is just to show kind of what the symbol is that's appearing. It's just going to be some factor that depends upon like the conformal factor on the sphere. And just pointing out that on the saddle point, you can see where the z versus z bar component are picking out plus or minus velocities. So that's just a little quick side. So when you see these subscripts, these correspond to the velocities. And the fact that there's only one appearing when technically there's a sum of polarizations is explained by this, just so that's clear. Okay.
And this x became pointing to ZZ bar point on the sphere by stationary phase. This is the logic.
Yes. Yeah, that's the only one. Great. Okay. Okay, so this is it for the gauge field, and then I could do the exact same mode expansion for CZZ, but it's just going to end up giving me a different prefactor right here. So I might just, we can assume we can do that. And basically the polarization tensors are just like 2 copies of it for CZZ and CZZ bar, Z bar. Great. Okay. So now I want...
It's possible to do reverse Fourier transform as well, specifying the gauge field at infinity.
So
and reverse getting the gauge field everywhere else. Does it work like this, or?
I mean, so definitely we go back and forth with Fourier transforms and the frequency coordinate, so that we can kind of regulate what we mean by taking omega goes to 0. I mean, in some sense, if you're trying to say that there's a mode that's at null infinity, I think this is similar to what we had talked about, like yesterday when people were talking about, that there's just the coordinates, like an embedding of the world length we're talking about as being on null infinity. I think this is the reason why when you have that expression, there's only a frequency
My question is,
part. And
is
then
anything lost by taking this limit, or you have full information about the field?
we would hope not, in the sense that this should be like, this is like the leading term in the gauge field. So as long as you can go back and forth between, like this is a statement that the photon propagates to that point. And so like if you're going back between a condition of like a phase space on null infinity and a phase space at a Cauchy slice, then at least there should be a way to go back between the two. But I agree with you that this type of saddle point approximation would seem like you wouldn't just be able to say that this is the mode. But in a sense, what we're basically saying is that it picks out a certain frequency. So you have a mode in a direction, and this is just a statement that this is like the zero energy component of that. So when I'm looking at
you
this
can
physical-
understand. Oops, sorry. You can understand it as a distribution on Scry,
Supported
along the
at-
generator
exactly.
C3.
And so as long as you interpret it that
all
way.
Fourier coefficients are recoverable. From
Yeah,
this.
I mean,
Mhm.
it's essentially the same sort of the same delta function that Eduardo was writing down yesterday afternoon, but you're making the delta function explicit.
And so this is where you still have the frequency component like here and the delta functions and the directions. And you can see that from the stationary phase. But I mean, technically, at least from this data, except for the fact that we now have the different frequencies, we do know what direction we're looking at and what field we're looking at. So in that sense.
Yeah, so you can also
Right, these are the physical
regard.
laws of the radiation.
Sorry, yeah, you can also regard the delta function data at null infinity as being what you put into the Dynamo integral form characteristic data.
So we have our modes. Great. So let's write out what the soft factors are in this case.
Did anyone know how anywhere analog of Bloch boundary propagators for this case of Minkowski space?
Well,
Well,
in
that's
this
a-
sense, we're
that's
looking at this as
so-
like the outstate. I mean,
It's just an exercise. But is it
I think it may be in Hoffman and Maldacena.
you could also just think of this as like literally, I mean, you know what, we literally took what you would think of as being your plane wave modes, right? And we did something to it to just look at its value at the, right? So in some sense, it is like evaluating, right? If you had some correlation function and you took like some convolution of one of the modes, it's exactly what we're doing, one of the mode we're taking. So technically it should be, I mean, if anything, I would say that this is evaluating the position space interpretation of that, and so this is kind of giving us that one-to-one. But I mean, like literally, this is the standard mode that you would have for like what you start off with just on your space, like Cauchy slice. And so like you basically have that because you just take correlation functions with something that you haven't taken that limit to, and then the A's and A daggers commute the same way. The delta function. Okay, so we have the mode extension, and now I want to look at the soft vectors. So, great. So the next step is just to write out explicitly, I guess, what the soft vectors are for a set of out particles with an additional soft photon inserted, or any gauge field. So in particular, the soft factor is going to be different depending on the theory. Okay. So this is the top part of the triangle that we're just kind of taking as starting point here. And I'm going to write out what these guys are. So kappa squared is 32 pi g, but it's sometimes it's easy just to keep track of it or set it to 2 and when a pi g is 1, so there's different conventions you might see in the literature on this. And then for everybody else, we have something here. So basically written down these expressions for the soft factors. And what I want to now look at is basically we have here what the mode extension for AZ is, or AZ bar, in terms of these AZ-made errors. So when we have a setup where we're looking at something, say like a ward identity or whatnot, where we have some out, here's some Q plus or S matrix, a different charge acting in. If we interpret this Q, which involves, say, for instance, if you look at the line with 8 pi GQY is that expression, and use the constraint equations, there's going to be a part like we discussed yesterday where you have the radiated fields and then some matter fields. And so we want to literally kind of think of inserting this mode expansion into the S matrix element and pulling out these soft factors. And what I'm going to try to show today is that it's a bit of like expectation value interpretation. So these are going to give you, with some differential operators acting on it, just like the radial electric field for a boosted charge. And so it's kind of nice to see that because it connects this picture of where these ward identities are coming from. And then so motivates this notion of how like the memory effect is like the step function compared to an overall shift that's just the pure gauge for these large gauge transformations. So we have our soft factors. We're going to do a charge expression like that. So let's get to it. Great. So right now I'm just going to write down.
Sorry, what is J?
Oh, J is angular momentum. So that's kind of cool thing. So we have 3 iterations. One of them is the electric charge, which is just this guy with polarization tensor momentum. Then the leading and subleading gravitational soft factors are going to correspond to super translations and super rotations. And so because they correspond to like the momentum and energies as like the globally conserved charges, and now this is like each particle is probing like that aspect of it. That's where you see that extra soft factor. So like you have this U1 guy here and an extra prefactor of P dot E, basically, and in that case there's a J that comes in. So it's probing that because a different order of Q appearing. But yeah, so great. And it's going to be nice because you can see this with the memory effects. So that's what we're getting to. So over here, we kind of already know what our conventions are. And so I'm going to add the charge for the other two right above the charge for. So there's some interest yesterday in the charge for the electromagnetic case. So I can just put this down. And then similarly for the bonding mass term, we can write down the plus G. Great. So right now, let's just look at those 3 equations.
Okay, and again, I just want to make sure I'm understanding correctly. Epsilon in the top line and F on the second line are functions on the sphere.
Exactly. So basically what happens here is normally you would have them go to a constant and you would say, oh, this is the electric charge overall. But the point is that now we have this constraint equation here that we're going to look at kind of every angle in some sense. Now, the subtlety is that, so in this case, it's just a function of the sphere, so there's a sense in which we can actually look at this at every angle. Same thing for the bonding mass term once we plug in the constraint equation. So like you see here, this became an integral over U with the partial derivative pulling out from this guy. But in this case, there's some YAs and DAs, so you might worry about like how arbitrary the prefactor is. And so like there's a sense in which only Y holomorphic, otherwise you like, so there's some kernels on that might make that a little bit more subtle. But yes, F is an arbitrary function corresponding to the super translation extra symmetry. and epsilon, same thing with a large D1. So that's, in a sense, that's why they're kind of similar to each other intuitively. And in the memory effect, I'll show the difference in some sense of like the observable that you would construct from those two cases. Great. Okay. So we have this U1 expression here. What we've done is, let me clarify a few things. So when I write these A's, I'm writing out a particular mode in the 1 over R expansion for the actual gauge field. So AU is the 1 over R term in the U component of standard, the A, with the gauge condition that A sub R is set to 0. So that's choice. Then AZ and AZ bar both are just order 1 fields, the radiated fields are order 1. And then FRU here, it would just be dr of A sub U. And because it's the 1 over R squared component, the electric field, this is the Coulomb field, 1 over R squared, this guy just corresponds to AU here. So that's why we can just plug this expression in, integrate it over sky plus, and then plug into the right-hand side from this guy. So just to note, these are stripped of powers of R, just so, and I can write out explicitly. Good. So you do the same thing for the supertranslation case, turn it into DUMB, you can plug this guy in, and yesterday we talked the same thing for the superrotation case using these guys. So use constraint equations to rewrite charge in terms of radiative modes and like what is leaving the infinity the matter part. Great. Okay. So the other way. This is where.
And the question of charges, is there any issue of is the charge Hamiltonian or something?
So,
is there
yeah,
something
so
like
that's
structure,
the
infinity?
that's the origin of the derivations of the charges, like in Varnich, and like you can look at like basically also like this symplectic structure. You would expect like the brackets, Poisson brackets for the position space fields along null infinity, and also check that the way that we've done this mode expansion gels with that. But yeah, so we basically started from like a lot of work by Varnich to like get to those expressions of the charges that, and there's some issue because normally you have just the variation of the charges well defined, so whether or not you can integrate it to an actual charge. And there's some subtlety also about it being null infinity in the sense that these guys have stuff that fluxes out because you're looking at slices that are null. So there's like a little bit of subtlety there when you look at the boundary. But essentially, you can see where it is like the origin with, if you just set epsilon to a constant, this is what you would expect it to be. So it builds with that. And it is coming from more thorough analysis, like Walden Zupas is a good reference too for how to handle definitions of charges. Great. So of this, soft factors and free factor, it's going to appear. Great. Now, you can get to Great. So now we get to play around with memory effects and just kind of seeing what these soft factors actually are and where these word identities are coming from. So it's actually good at this point to imagine massive scatterers just for the moment, because when we look at the soft factors for them, you can see some more kind of like classical electrodynamics results in intuition. So right now I'm going to write gamma, what I mean by this is Lorentz boost factor for corresponding to the velocity of the guy. So this is slightly different notation than above, but it's kind of maybe I write gamma sub beta to keep that into account. So this is how you write the momentum massacre. So now we're basically going to plug into the soft factor this for momentum for like a single charge. So this soft factor is the sum over the external photons, say, attaching to the different legs, and this is just looking at the contribution from one of those legs. So just say plug in a single one. And essentially from this equation, we can get what we expect for a relation. For the massive guys, none of the charges are going to leave through null infinity. So along null infinity, you basically have a relation between the radioelectric charge and the radial field from the electric charge, however it's moving, and the radiative field that happened. So write this down. So you have an expression like this, like delta AZ would be equal to, give it 4 pi. So this expression right here is a statement that just from the mode expansion that I have. So I've plugged in what A is and I've looked at. It's the step that it takes. So basically this is looking at some integral of du of A, giving the delta. And this is just the soft factor times the factor of omega pulled down from the du derivative. So this is just from the mode expansion. Right. And now, what's kind of fun is if we take...
I didn't understand why soft factor appears in the mode expansion.
Because this is like when I wrote down the mode expansion before, and we had that like A sub z is equal to some prefactor coming from there. And then A plus say minus of omega q. Except u. Right. So I've plugged in this expression into here. And then, because I'm evaluating delta A, which is the integral of this guy over u, so I integrate it to du, then I'm basically going to pick out du of this guy is going to pull down a factor of omega. And then the integral is going to basically have support, like a delta function support at omega goes to 0. And so there's some subtleties of like which order of limits you choose in the sense of like you regulate it by like writing like some e to the I omega u du like as this omega goes to 0 to pick out omega q is omega or something like that type of thing. But otherwise, essentially it would make sense that the long time interval is going to pick out the zero frequency part of the creation operator. So if we now literally interpret that as you take the limit after, so like you would evaluate this and limit as omega goes to 0. That's
but all that was for a single photon, and soft factor is more complicated logic, right? It's
So
single photon attached to other stuff.
So that's the confusing thing. So this is like a single photon, and the soft factor is going to be sourced by each of the lines of the scatterers. So we have some, in this case, massive charges, say, and then we have a photon coming out of it. And so the soft factor here is the sum over all of those guys. And so in the sense, this is now inserted in the scattering process. So the scattering process, when A hits each of these zero lines, is exactly what is going to end up. Right, so we have this picture of, in the Feynman diagram, you have like something scattering process happening, and then you have the soft guy attaching to each of the legs. Right, so I'm drawing different possibilities, and then like you hit some of this one with that one, and so essentially that's the different sums in terms of the soft factor. And what I'm saying now is I'm just going to look at the electric field configuration for a single charge that's boosted. So they have a set of momenta, and I'm just going to plug in a single component of this guy, which is the sum over that. And so if I do that, which is kind of fun, so 0. So I'm going to do this. What I end up getting out, which is very nice to see. So let's turn a little bit. I've taken the soft factor, which is the sum over, so that's O minus the sum over the electric charge times P dot epsilon over P dot Q. And I look at the particular, so this is M over PKs, I look at the particular contribution just from P. So I don't worry about the sum, I just have a single particle and I plug in the soft factor and act with this differential operator on it. Then I pick out just this guy. And this guy should look familiar for just looking at a boosted charge electric field. So basically what I'm saying in the following is that this is one of our stripped component of just the radioelectric field for a charge that's boosted with this velocity, and you're in this direction, you're looking at it far away. So, upside of this is basically soft factors are just, in some sense, like these memory effects are telling you just this is the final state of, say, a charge. And so you can then interpret this equation as saying you have, in this case, the radioelectric field changes because you have some in particles and some out particles, and the amount of radiation that you observe is just corresponding to the change that happens. So in some sense, what I want to say is that when you have these memory effects, there's a kind of final state and initial state that you specify by having the scattering process, and that will constrain some amount of radiation that you observe just because of the fact that you have this net change in the fields. So you have this guy for this, and you can do the same thing for the massive case. When you're looking at some bonding mass term, then essentially the expression that delta MB is the 1/4 dz delta C dz. This is that expression from the constraint equation, and then what you end up getting out of it is just literally evaluating Weinberg's soft factor for a single particle contribution. So basically what I'm just saying is that the soft factor is, again, just telling you what the expression is for a boosted mass for Hertz. Basically.
Is this interpretation important for the later, or it is?
Well, I mean, because kind of it's a cute result. But the fun thing about it is, the reason why it's important is what I'm saying is the following, is that you can see that this is just a contribution from a single soft particle. So what we're looking at in this case is the radiation that comes out. And the radiation is going to be related to basically the fact that there's a change. So you've set, this is the initial, and then there's a final for it. And when you have incoming particles and outgoing particles, there's a certain amount of radiation that also comes with it, no matter how you get to that point, in a sense. So that's what I'm saying. The origin of memory effect is because of the fact that you have this, like, radiation is conditioned by the constraint equations on the initial and the final states. So this is just showing that it's coming from boosted charge, and you can see, like, oh, look, I have some set of charges. It started this way and they end this way, and then I see the radiation from it. And so it kind of simplifies, like, what the origins of the things are, because you kind of, like, this is like what you've seen before. So it's like, yeah, I know this. Yeah. No?
Do people understand this?
Oh, no. No? Come on.
Sorry.
No.
Somebody explain it?
Okay. Do you understand this expression, hopefully? Or this expression? We got this one?
Oh, yeah, this is a simple expression.
Exactly.
But all the steps.
This is another point, is getting it to a simple expression. So, okay. We have an end state, and it's specified by some momentum, some velocities, and some charges, say. And basically, these memory effects are corresponding to supertranslations, superrotations, and the OLRG1. So, in the sense that if you just looked at a charge, and you looked, it's boosted, some velocity. So P and Q are telling you Q and the direction that it's going. So this would be its radioelectric field if it were just moving with nothing happening. So in a sense, what happens is in the soft vector, you have a sum over in minus out, or out minus in, depending on your choice of sign convention. And what you're doing is you're taking, basically looking at the fact that there is some radiation that you observe because of the difference in these final states. And so all I'm saying is that the soft factor, which is a measure of the radiation, like this extra soft particle, say you're looking at the gauge field, that's the 1 over like the A sub z component, is just telling you from the soft factor that you have some net change in the distribution of charges due to the in and out states. So all I'm saying is that, like, you measure some time interval of the gauge field when you're sitting.
You're interpreting soft factor as electromagnetic field.
Exactly. That's all it is. Exactly. No, but I'm interpreting it, the soft factor is that to tell us that we have this memory effect. This is just the origin of it. And the same thing for the gravitational case. And the fact that those two do seem rather simple means that we should expect a similar observable for the super rotation case, and that was something that is kind of mirrored.
So these deltas here, the delta is just the jump from I0 to I plus.
Delta is the jump for the whole time that you're integrating along the radiation. So I0 to I plus, or you would include I minus to, it depends if you only look at retarded radiation or some combination of incoming.
Yeah, I was just thinking.
Yeah. But it's basically, so if I just looked at I0 to I plus, because right now I've written everything just in terms of, I think matched to Pascal infinity. I just would think of it as like, say, only outgoing radiation in this flow you get. So it's kind of nice, simple interpretation. But the point is that it really is just telling you that there's some radiation that I'm observing that's just depending upon the changes in the initial and final charges. So that's all I'm trying to emphasize, is that it should be hopefully simple.
Yeah. But I'm just getting slightly confused because the memory effect I think of as being the net super translation.
Yeah.
But you haven't integrated to find that yet. So that's
No, so what I want to say is the following: is the memory effect.
I mean, so or
It's
the
a
net
net
base
displacement.
transformation. I mean, if you
So this is what I want to emphasize: is that there's a physical observable, and then there's the pure gauge part. So
Yeah.
okay. So let's.
I mean, there's a gauge transformation which takes you to sigma equals, CZZ equals 0.
Exactly. Wait, so maybe let's see. Let's make sure we're on the same page.
The
So what I say is the following. Say I'm sitting near null infinity, and I have some like set of masses, and then there's some profile, and then it jumps. So in a sense,
So what are you drawing?
I'm drawing along. Sorry, I'm drawing. Okay, maybe this isn't the best. I'm just time. I was just gonna like retarded time roll in a null direction just for the sake of matching the diagram, but I can just do it this way. So at any given angle, so say I fix z, then I can imagine that there's nothing, and then there's some jump, and I have this arbitrary function in the sphere, so I'm just drawing that this function has changed. And so if I have a set of masses, this would look like they move by a little bit from where like they were initially just set. So this is like two different angles in this one. Right. So for the super translation case, you can think of the memory effect as you have a set of masses on a sphere far away that are test masses, and then you can look at, say, like geodesic negation equations and see that this net result of the radiation coming is just going to be some net displacement of those masses. And so like that's the memory effect. Now, the connection between super translations versus that is that.
And you've got a Laplacian squared or something you've got to integrate to get to the super translation from the delta MB.
For the delta MB. So what happens is it depends on whether the super translation is just this right hand side, is what I'm saying. It's this delta CZ.
Well, CZZ is the shear, and the shear is the second derivative of the, in a flat region, it's just the second derivative of the.
So when you have R, you can work out the geodesic deviation equations and see that the CZZ term, the delta CZZ, is basically going to give you the super translation. So when I write
you can integrate that to get the.
But the two derivatives on C is the change in the shear when you apply a super translation. Right? The shear changes by.
So super translation is this pure.
So delta CZZ must be the super.
Delta C is
no. C is the shear.
What's the delta in front of it?
Delta is the change over the angle.
So that's given by x squared.
That's right. Yeah. So the overall formula is delta of n is equal to the Laplacian square.
Yeah. We have DUMB as DUC. This is the constraint equation. When you look at the second derivatives, and then it's like order of like how when you integrate out when you look at the Riemann tensor and look at geodesic deviation type interpretation. But if you quite literally just plugged in this constraint equations and solve for delta CZZ, that you can think of that as looking at the change in positions too. That ends up working out to being that.
And then the formula below is the contribution to that from the soft factor.
Exactly.
And that's the idea is that that's the.
And the idea is that's coming from the fact that you have some net changes in the final versus initial state.
Yeah.
And so in the case of the Ward identities and whatnot, we have the matters leading through null infinity. And so this bonding mass term has been matched, or it goes to 0 at the future boundary in the past.
Right.
And then the rest of the source is coming from this stress that's stressing through null infinity.
So that formula is telling you that you have yeah, I mean, you could understand that as saying that you've got a total mass in the space-time at I0, and then as radiation sort of comes out, that will maybe drop to 0, so you get a delta m,
That would,
and then that delta m is Laplacian squared of the sort of the super
You can look
translation
at the
from the
source
fact
thing of
coordinates
it.
near I0 to the fact coordinates near I plus.
yeah, I'm saying effectively you can look at, you just want to look at, so in some sense if you look at the C is going to change. So if you look at, say, for instance, say you started in flat space, where it's 0, and then it changes to something else, you've moved in the sphere too.
Yeah.
So that's another interpretation of it. And you can try to derive the fact that this actually is like this net displacement by looking at geodesic deviation equations. And that's a slightly different format from this. But in this essence, you can kind of look at what's the final state of the metric as a result of this. And that's another way of interpreting it. So that's where the delta CZZ is basically saying that there's a pure super translation part, which is an overall shift, and then there's a step function part, which is like the fact that things have moved, and that's the physical memory effect. And we can see the physical memory effect corresponding to self factors is basically because you have some net initial versus final velocities of charges or masses. Okay, so the super translation is similar to this. And then the U1 gauge transformation is similar in the sense that you have a function of the sphere again, but in this case we're looking at a gauge transformation. So the point of that is that, say you're sitting along null infinity and there's no radiation that comes in, and then some radiation comes in, you have a step function, and in the intermediate regime it looks like it's pure gauge in the sense that you can use these large gauge transformations to just shift it to 0, set your baseline again. So what I'm saying is that the residual like large gauge symmetries that we're saying are somewhat more important are basically within the same order of magnitude as the step that happens in a typical radiation process. So there's no canonical choice of like 0, like saying that, oh, this is exactly at every point, say some specified 0, because if anything else happens, it's generically going to change. So that's kind of the origin of some of the arguments for why these particular pure gauge are slightly more interesting. Okay, good. Anyways, the self-factor thing, I like to look at the masses because this is something like, oh, this is just a boosted charge. And then you have the fact that there's some final state and some initial state. And as the constraint cases are saying something else radiated in between, and that radiation you can actually measure, and you can think about how am I going to measure it. So this is a good point to then get to the final part, which is, okay, so we kind of know how to measure this Christodoulou memory, or I guess also Zelovich and Polnarov, where you see that this net change in the metric is giving you some displacement of masses. If we want to look at the electromagnetic case, we have that what we've integrated over time is just the radiated electric field. So if you had a charge there, it would give you a net kick in its velocity. Or you could imagine some effective, like putting it in some like liquid where it's like very viscous, and then you have, instead of like x double dot is equal to the force, you just make it some like sigma v, so it's damped, and you could have a net displacement. So that's like a way to measure that effect. And so now let's think about how to do the same thing for superrotation, which is a spin memory effect. And the essence of that is basically we have this profile that has stepped up over time. So when we're looking at low frequency observables, we don't want to integrate something that's constant over time and you get something divergent. So the cute thing is to pick up a chiral observable that basically projects out per super translation. So pure super translation, we would have CZZ equal to UZ some function on the sphere. And so even if this profile ended up being like some physical process, which we have this step function again, then at late times it would still be whatever value, say C here, of infinity here. That. So if we look at a chiral observable that, say, projects out this part here with like with the curl, then we can actually construct or extract a subleading self-factor term that doesn't have a divergence that would come from integrating something constant over U that's changed. And that's going to be what this spin memory effect is. So just a quick expression for what the spin memory is, just to get a sense of that. So if you literally plug in for the metric, so it's a little bit artificial at first because what we're looking at is, say, for instance, a ring sitting at fixed coordinates and Bondi coordinates. So there's these, and you look at the infinitesimal deviations in Z, and say that it's a massless trajectory. Then what you can work out is that if you have two, say you have a counter rotating ring, and you send one beam one way, the other beam the other way, and you look at when they meet up, if there's a time delay between them, then on a single circuit, you're gonna get this. For the accumulated time delay between the two guys on this ring where we said we'd fix the coordinates. And then what ends up happening there is that you get this delta U retarded time if you wait and integrate that over a long time, because basically what I'm saying that every time you go around the ring, you pick up a little bit of delay, and then if you integrate over time, you're basically sampling that every time it's going around the ring, so it turns into a integral. And so what I mean to kind of point out in an equation like this is that we've constructed something that's an integral over u, so it's going to pick out some zero frequency component of this mode expansion if we plug it in. So that's potentially a memory effect. And also, it's because of this curl, if you can use an appropriate Green's function and basically take this expression for nz and turn it into a relation between nz and tuz. Basically, this term becomes that guy when you integrate over the whole region instead of just the contour. And so basically, you have an expression where angular momentum flux gives you what you can interpret either as a time delay if you have these fixed bond BMS coordinates, or in a sense would be like a Sagnac effect and the ring would rotate if it was geodesic. So it's kind of cute that basically the intuition from what the memory effects are and how to like pick out what the like zero energy observable is for the other soft factors, and the fact that we have this triangle and we expect to also see something for when we have this new soft factor that Freddie and Andy worked out. And also super rotations is like a potentially extension to super translations that are at null infinity. Then what's the memory effect? And like that type of logic leads you to this good memory effect, which is just either time delay or a net rotation. So any questions at this point? There's a little bit of a teaser for the talk we get tonight, or today is the afternoon. It's actually kind of fun to think about. So the memory effect is basically telling you what happens. Say you have some charges accelerating, you see the radiation, and I wait a long time and I measure the radiation. So then what happens if you have a horizon? Then anything that falls in, you wouldn't see the radiation due to that acceleration after that point. So you can imagine that like it's a fun way to like think about how would the memory effects play out in this situation where basically there's a shadow to what you can see as an observer at null infinity. And so then you'd imagine if the final state were really hairless and had just some like say electron positron fall in, you would see maybe final state that was neutral, initial states that were the initial momenta of the electron positron or whatever, maybe black hole that was initially there. And then that wouldn't necessarily gel with what you see as from the accelerations of the trajectories, because as it crosses the horizon, you wouldn't see radiation after that point. So that's just a way to play around with what would make the horizon kind of natural in that perspective, but also that's where things go awry when you try to convert between a Cauchy slice and null infinity, unless you have something else coming into play. So it's a bit of a teaser, food for thought. Any other? I'm good. That's what I want to say.
More questions?
Perhaps a naive question. Just does any of this, you know, if you add this maybe small cosmological constant, like
so okay, I don't, I haven't worked out the details, but technically, naively, what I would do is I would go to a patch where effectively I can do the story and kind of like surround my region and then propagate freely out of that using the fact that there's now a cosmological constant to change what the propagators were and see where it would go. That's like how I would picture it. I would patch together the flat space like region where it's effectively fine, say that the scattering occurred there, and then say that it's now these outgoing states or incoming states are free modes that propagate in your curve. Sorry, but I haven't done that. but I think it seems reasonable. Because then the boundary is going to be different, and you have different symmetry groups. And it's probably more interesting to look at some ADS things. Okay.
Actually, coming back to the subject, so is it understood what happens with super translations? Say, if you embed this causal diamond inside the ADS?
They see normally what happens is they study just directly the symmetry groups of like the space-time itself, not this. So I haven't worked it out, but I'm imagining that at least for the memory effects, you should be able to just do that. But I think in essence, like nobody used to do with the symmetries of the boundary, so you would have.
The question is infinite dimensional group versus finite dimensional, right?
But you definitely do in some of the ADS3 stuff. You get some full of it.
Well,
too. I mean, like it's different. It's different. Really
This
different.
is rigid. But this is kind of going to find it's only got a finite dimensional group. I mean, I don't think.
So what will happen with super translations if you embed a piece of Minkowski space inside ADS?
Well,
But I mean, to have the super translations, you don't just have Minkowski space. The way that you're talking about, you have conformally compactified Minkowski space. So what does it
So you
mean
have
to
this
put a
perimeter,
conformal
there's a
boundary?
boundary.
I mean, the point, the reason this is happening is because the vowel tensor is actually, you know, in a conformal context. But the reason this is happening is because the null infinity is a light in which the vowel tensor vanishes, and so that is very special. And it's only at that point that you get that symmetry. I mean, otherwise it's you know, it has local invariance and there's no symmetry.
It's similar to talk about approximately vanishing, right? Just a very small piece of.
But there's a sense in.
But it vanishes exactly here,
Okay.
and then you have exact symmetries. And I guess if it's only small, then I guess you would have. I'm not sure.
I mean, well, all I'm saying with the statement with the patch is basically saying that like there's something particular. I mean, like so, like. Okay, when you have this conformal form of activation, you've taken all of the Minkowski, you've drawn it in this diagram. There's a sense in which, like, anything that happens near the center of it. So if I then tried to like propagate further outward, it would be saying that there's a special point where this interaction occurred in some sense, and probably that's where things also break. Because you're saying that there's something particular about that boundary, and you could imagine a region that's special because you said that you're looking at the scattering.
Yeah, the reason
And that you wouldn't have that if you had the full space where you're not having that like region that you're looking at, in the sense that you can't just like, there would be no kind of way to like, hey, this patch is the Minkowski space patch that I'm propagating outward. Is what I think I would translate between what I said before and what you're saying.
I'm not sure. I mean, all I'm saying is that symmetries are a local thing. It's a solution
And
to
you're
a
saying that
killing type of equation. And the reason why that those equations are actually sort of locally integrable along scry is because the vowel tensor is vanishing on scry. If the vowel tensor was really small, then you'd have small obstructions to integrability, but you know,
And also-
an obstruction is an obstruction.
No, but we also have only outgoing, say, radiation along future null infinity and incoming along
I mean,
the
there
path.
may be
So
some-
that's what I'm saying. Like,
These
there's a
identities do
statement
have analogues. I mean, you know, I guess if you just want to sort of say that the outward going radiation, I mean, this is what you're trying to say.
So I'm
isn't it?
saying
you're
if I
trying to say
make the
if you have it,
measurement. But
if you have something crossing a surface, it doesn't really matter if it's
where
if that surface is curved or not. You
Exactly.
might still get these shifts.
So what I was making the statement is that we can, even if, so they say there is a cosmological constant in space-time, and we look at a patch, we can like do this type of analysis near that patch. But then to gel in with this, like the reason why when you study asymptotic symmetry groups of other space-times you don't get the same thing is essentially what I'm saying is like there really isn't a natural like patch in the sense that it's only outgoing near the like one boundary and coming in the other, and like looking at that region and then just propagating freely outward that wouldn't necessarily like fit into what you would expect from the like asymptotic symmetry group of the full space-time where you don't kind of imagine that particular Minkowski space patch.
I think the way you're supposed to think about it is in terms of what you personally can observe. That is to say, you should be thinking about the effect of soft photons or gravitons or whatever crossing your class light cone. That's really what you should be considering. And then, of course, you still have the issue of what the gauge transformations are on that particular surface.
But I mean, you know, just because it doesn't have exact symmetry, it doesn't mean that you can't sort of maybe attribute some
No, there must be nothing
shifting.
like that.
Shifting. You know, there's still a geodesic.
You still
I mean,
make it-
you're
you
talking
make
here
it
about a
exact.
geodesic deviation equation
Exactly.
Right, but there is
and
still
integrating the effect
You would see
of
that.
outward going radiation on a bunch of co-moving observers along the light path.
Right.
It's like what he's saying.
Lots of observers can say light rates, but anyway.
Right, but I mean, that means, of course, that different observers will see different things. That's the thing you have to get.
No, but that's fine. If you're
Yeah,
interested in
it's
cause, if you're interested in causal dynamics, and of course the cause each core diamond does its own thing, but
Right.
it's not
The
uninteresting.
thing about here is, you see, that
This is
because you're looking at scry, it's something which
It's
is rather has
universal.
more objective meaning.
Positioning of system.
But what you say is very reasonable sounding, you know, it might well be the right answer. It's an astounding answer as well, right? If you're saying that I'm in the middle of some space-time, but it's the boundary of my past lifetime, which is just some completely irrelevant thing as far as you're concerned. Shouldn't I just query all transformations that are on that?
Well, there's a question also of which direction. I mean, like if you're sitting at null infinity, there's a sense in which it's outgoing too, right? So there's something a little bit special about that. Like you don't expect something to come from one way, but if you, yeah, right, it's a little bit of that.
But normally, I mean,
But there are no transformations because it's got curvature and it's sort of there's no local symmetries. I mean, yeah, I guess
This is the opposite of the memory effects. That's kind of
but the memory effects could be traced,
Effectively.
could be reformulated as some statements
the
about
radiation. Is
about the geodesic deviation equation and shifts.
Exactly. Yeah.
So no, I'm not sure. I haven't pieced that together in my mind, but I'm just guessing that you can still talk about it in that language. I mean, that was the language in which I guess people like Budviskin and
They actually make it more formal that way. Yeah.
Prasoon and so on
Yeah.
phrased it.
Okay, thanks, Sabrina.